Here is a typical Newton's second law problem, rather straightforward problem. It's a two-dimensional problem, and if you think about it a minute, it's sort of like an Atwood's machine with one of the weights on an incline instead of just hanging freely. And the incline that I've chosen again is 37 degrees, but there's friction between the 5 kilogram object and the incline, and the coefficient of kinetic friction is 0.2. So choose a body. I will choose the 10 kilogram object. Okay. And what are all the forces on the 10 kilogram object? Well, there's its own weight. Which is 100 newtons down. Okay, and there is a tension in the string which is up, and that's all. And I will choose plus y to be down like this. And so now this part of the problem is a one-dimensional problem, and so we can say the sum of all the forces in the y direction is equal to 100 minus t, and that's equal to 10 times the acceleration. So now we have one equation and two unknowns, so we have to choose another body, and we choose the 5, and the forces on it are a 50 Newton weight, a normal force N, the tension in the string T, and some frictional force F, which I draw this way because you'll notice that I've specified that the 5 kilogram object is moving up the incline. Okay, choose a coordinate system, and so I will choose, let's see here, I'll choose my plus y like this, and plus x like this. Notice that I have carried through with the rule of the finger. That is to say, this plus x is along this way. Okay, so here's plus x here. And then I've come around the pulley, and for this one over here, we chose plus x like that. Okay. Resolve all your forces. Well, three of them are already resolved, but we've got this guy, and I will leave it as to the student to convince yourselves that this is 37 here, which makes this 40 and this 30. Okay. So now the sum of the forces in the y direction is equal to, in the y direction, this guy is in equilibrium. His acceleration is only in the x direction. And so this is a Newton's first law problem here. And that's equal to n minus 40. So we find out that the normal force is equal to 40 newtons. And therefore, the frictional force is 40 times 0.2, or 8 newtons. Okay. Now the sum of the forces in the x direction is equal to 5a, and I can write the same a because I've used the rule of the finger. Okay, and this is equal to t minus 30, that's the x component of the weight, minus the frictional force, which is 8, and so we have that 5a is equal to t minus 38, and we have that from the first body, we have that 10A is equal to minus T plus 100. And so 15A is equal to, this should be minus T, not minus 10. I said minus T, but I didn't. So if now add these two equations, I get 15A equals 62, or A equals 4.13 meters per second squared. And if I take that and put it into either of these two equations, I find that T is equal to 58.7 newtons. And the problem is now complete.